In this video, we're going to review quickly the exam 4 topics, or the typical exam 4 topics. We're also going to go through the Hibbeler crib sheet. Since Missouri S&T students are allowed to use the Hibbeler crib sheet on their exam 4, it's important for you to understand what's on that crib sheet, what's not on the crib sheet, and how to use it. So these are the topics on a typical Missouri S&T exam 4 for statics. There's 4 sections. The first section is fluid pressure, and we'll work some examples of those later and go through some of the principles of those later. The next section is area, moments of inertia, IX, IY, and you need to be able to integrate for those and find IX or IY for a composite area. The third section is product of inertia, or IXY, and you need to be able to integrate for that, or at least set up an integral, or since it's a multiple choice test, recognize an integral that's set up for product of inertia. And then finally, product of inertia for composite areas, how to calculate them, with understanding what the signs are for product of inertia. And the fourth section is Moore's circle. And usually these are simple, straightforward problems that I've addressed in a different video. But these are the 4 sections that you need to be prepared for. So let's look at the crib sheet. And so this is crib sheet page 1. And the exam 4 topics that are on here are fluid pressure, moments of inertia, transformation equations. These are the 2 theta form of the transformation equations. Moore's circle down here. So let's talk about these formulas. I'm going to pull up my notes. So first of all, the fluid pressure formulas. They give pressure is equal to gamma times Z, or rho GZ. He doesn't give the gammas. You should remember that for fresh water, gamma is 62.4 pounds per cubic foot. And again, gamma is a specific weight. Rho is a mass density. G is the gravitation constant. In the SI system, the mass density is 1,000 kilograms per cubic meter for fresh water. And that rho times 9.81 gives you a specific weight in the SI system of 9810 newtons per cubic meter for fresh water. These are the most common numbers that you see. If you're dealing with an oil, the gamma will be less than these, maybe 56, 55 pounds per cubic foot, 800 newtons per cubic meter. If we're dealing with a weighted fluid, like a drilling fluid, the gamma might be 65 or 68 or 70 pound per cubic foot. This gamma would be 1,100, 1,200 newtons per cubic meter if it's a weighted fluid. If it's a concrete slurry, your gamma can be up to 150 pounds per cubic foot. And I'm not sure what that would be, 2.5 times this, so 2,500 newtons per cubic meter not 2,500, 25,000. 25,000 newtons per cubic meter in the SI system for a concrete slurry. So read the problem carefully, use the gamma that they call for. But again, your crib sheet gives the pressure is equal to gamma Z formula. It gives, another formula it gives is the resultant force on a plate is equal to gamma times Z bar times area. But the picture doesn't show Z bar. We look back at the crib sheet and zoom in on this picture. So I give FR is equal to gamma times Z bar times area. But remember that it gives a Z1 here, it gives a Z2 here. But remember, when you're applying this formula for FR, the Z bar is the depth to the centroid of the plate. This picture gives FR acting at the centroid of this pressure distribution, which is correct. That's where FR acts. But again, to calculate FR using this formula, The Z bar is to the center of the plate, which is like right here in the middle. So it doesn't give that, but you need to know that. And I note that on this page here. I basically say the centroid of the plate is right there, and Z bar is the distance to that guy. So you just need to know that anyway. Another formula that's given on the crib sheet is the formula for the composite method. And by composite method, we basically mean if you have a curved surface, you have to, the resultant force on this curved surface is equal to F horizontal plus F vertical. They actually don't give you the formula. I mean, they show you these F vectors, but it does not give you, go back to my sheets again, it does not actually give you this formula. So as a vector, the resultant force of this fluid, the resultant force of this fluid on this curved surface as a vector is equal to the horizontal vector plus the vertical vector. The horizontal force is the resultant force that this fluid would be acting on a vertical section that's equal to the vertical cross section of this curve. The vertical force is equal to the weight of the fluid above the curved surface all the way to the free surface. If the free surface is here, then F vertical is just the weight enclosed here. If the free surface is higher than this, and you have a curved surface and a straight surface, then in this case, F vertical is equal to the weight in area 1 or volume 1 plus the weight in volume 2. So he actually doesn't give this formula, but you need it and you need to understand it. Another thing he doesn't necessarily show, here he shows this weight is equal to the weight here, but up here he gives FAB, implying that this is the resultant of this pressure distribution, which it is, but it's also equal to the weight. And so this FAB is the weight of the fluid above this flat surface too. So you just need to understand how to apply these formulas. Finally, one more issue is center of pressure. He shows the center of pressure right here. So this point P is the center of pressure. And the center of pressure is basically, if you extend FR to where FR touches the plate, the point where FR touches the plate is called the center of pressure. And that's sometimes a concept on your exam 4. If you look at a curved surface, where you have a horizontal force and a vertical force, the horizontal and vertical force intersect here. The line of action of FR goes through that point, but the point at which FR touches this wall is P, and that's the center of pressure, where FR touches the wall. So that's a concept that you need to know, and that term is not on the crib sheet. Continue with our crib sheet. We have moments of inertia and product of inertia formula definitions here, and parallel axis theorem definitions here. All of these definitions for moment of inertia and product of inertia are only true for properly chosen DAs. These are not true for every DA. If you look at the moment of inertia equations for a generic area, Ix is the integral over the area of y squared dA, Iy is the integral over the area of x squared dA. And these are true for double integral, where your dA is equal to dx dy or dy dx. These are true if your dA is parallel to the x, if you're finding Ix, where the entire element is at some y distance. And these are true for a dA parallel to the y, for IY, where the entire element is a distance x from the y-axis. These are not true for other dAs. For example, a dA that's perpendicular to the x-axis or one that's perpendicular to the y. So you just need to understand how to apply these formulas and how to choose the correct dA. But again, in general, if you use the double integral or if you use an element parallel to x for Ix or parallel to y for Iy, then these formulas work fine. For product of inertia, he gives Ixy is equal to xy dA. And strictly speaking, that's only true for a double integral, where dA is equal to dx dy or dy dx. If you choose a horizontal element, then the I bar of this guy is 0, but your integral is an integral of x tilde y tilde dA, but for horizontal element, the y is y, but the x tilde is not x, it's the average of x left plus x right over 2. And then times your dA, which is x right minus x left times dy. So this is not xy dA. This is y x tilde dA for a horizontal element. If you choose a vertical element to compute Ixy, then the x is x, but the y tilde is the average of y top and y bottom. So y top plus y bottom divided by 2. The dA is y top minus y bottom times dx. So again, this is not xy dA. This is x times y tilde dA if you choose a vertical element. So again, strictly speaking, this definition of Ixy isn't true for every dA. It's true for a double integral dA. So you just need to know what you're doing. And you really need to be able to integrate with your calculator too, because occasionally there's a problem that shows up on an exam that's actually fairly difficult to integrate by hand. And I think the teachers expect you to be able to do it on your calculator. So be sure to practice that. Also on the crib sheet are transformation equations. And these are what I call the 2 theta form of the transformation equations that involve the cosine and sine of 2 theta forms. There's an additional set of transformation equations, which I call the theta forms, which are given in terms of cosine squared theta and sine squared theta. They're basically the same equations, that they only differ by using trig substitutions. This set of equations, the 2 theta forms, are the ones that are combined to derive Mohr circle. These guys are also easier to compute with, or to do calculations with. We don't usually have transformation equation problems on our Missouri S&T exams. I think we should. Actually, I think we should have a simple one on there, but we don't typically have it. But these are there if you need them. This term here is the radius of Mohr circle. This guy here is I average. And so the I max and I min formula is here, which is useful. If you take the IUV equation and set him equal to 0, because basically at I max and I min, the IUV or the IXY is 0. So set him equal to 0 and solve him. And you get this tangent of 2 theta p equation, which is equal to negative IXY divided by IX minus IY over 2. And this gives you the angle theta p from your x face to the nearest principal. You may need to do that. Also for Mohr circle, Hibbeler gives you this picture. This is actually kind of an important picture because it's not uncommon on one of our exams, since they're multiple choice, to have an area that basically says, that gives you multiple axes through an area. And it says, which one of these is I min or which one of these is I max? Well, the I min axis is the one that passes the most closely through the middle of the area. So if you do the integral of a distance squared times a dA, and all of the distances from this axis to the various DAs on this area are minimized, then this is I min, and then the I max axis is perpendicular to this guy. And so that's a common conceptual question, and it's on your crib sheet. Learn to read your crib sheet. There's a picture here for Mohr circle, which sets up Mohr circle, gives you the radius formula. The center is I average, which is Ix plus Iy over 2. This triangle is super important. So the coordinates of A is typically your x face. So the coordinates of A is basically Ix and Ixy. Remember, positive Ixy is up, negative Ixy is down. The horizontal axis is moment of inertia, which is basically your Ix, your Iy, your Imax, your Imin are all on that axis. Point A again is your x face, which is basically Ix and Ixy. He doesn't give the mirror image of A, which would be point B, which would be down in this lower left quadrant of the circle. Coming back to this sheet here, he doesn't give you this point B. If you extend A down, this is basic. If A is your x face, then 180 degrees from that is B, which is the y face. And so this would be Iy and negative Ixy down here. He doesn't show that on his picture. The distance between Ix and Iy is this distance here. And if you divide that by 2, you get the base of this triangle, which is Ix minus Iy over 2. And this triangle is something that we set up and use a lot in the conceptual Mohr circle questions. But keep in mind that this Ix minus Iy divided by 2 is also equal to Ix minus I average. And you could actually mathematically kind of prove it. It's simple to do. But if you happen to just have Ix and I average, then you can use this formula here as well. Another issue that's not, it doesn't say explicitly, but it's that you just need to know is that theta on the original area and with respect to the original rotated axes is equal to 2 theta on Mohr circle. And that just basically is a property of Mohr circle that comes from using the 2 theta forms of the equations, transformation equations, to derive Mohr circle. And so that's a principle that you need to understand. Oh, we skipped over this parallel axis theorem. So the parallel axis theorem is also on page 1. And so for moment of inertia, the parallel axis theorem, so the Ix or the Iy is equal to I bar, which is a centroidal I, plus an area times a distance squared. Remember that when you use the parallel axis theorem, one of the two axes has to be a centroidal axis, has to be an I prime. And then from that, you can go to I of another axis. If you're trying to go from an axis A to an axis B, and neither one of them is a centroidal axis, then you have to do it in a 2-step process. You have to go from A to the centroid, and then from the centroid to B. The parallel axis theorem for the product of inertia is Ixy. So the product of inertia of this area about the xy coordinate system is equal to the I bar x prime y prime. So this is the product of inertia of an area about its centroidal axes x prime and y prime, plus its area times dx times dy. And dx is the distance from the y-axis to the y prime centroidal axis. It can be positive or negative. And dy is the distance from the x-axis up to the x prime axis of the area, and that could be positive or negative. The I primes for symmetric areas, for example, a rectangle a square, a circle, a isosceles triangle that's symmetric about its central axis, a half circle which is symmetric about one of its axes. All of those I bars are zero. So for a number of different problems, the parallel axis theorem for product of inertia simplifies to just the sum of a dx dy. And again, that can be positive or negative or zero, depending on your dx's and dy's, which can take on positive or negative or zero signs. On the second page of your crib sheet, Hibbeler repeats the equations up here for Ix and Iy and Ixy. And again, I would add that these equations are exactly correct for double integrals, but they're only true for properly chosen DAs, which we've already explained. You need to understand these formulas for these areas. And I'll just go to my notes here. I've just kind of gone term by term. So for a rectangle, the I bar is 1/12 BH cubed. The I base is 1/3 BH cubed. It gives you an I bar XY, and that's equal to 0 because it's symmetric about the centroidal axis. He gives an IXY product of inertia, which I call an I origin form. So if the x-axis and y-axis touch this rectangle, then the product of inertia of this rectangle about those axes is 1/4 b squared h squared. But what he doesn't give you is if this rectangle is in the quadrant 2 or quadrant 3 or quadrant 4, then this equation will take on different signs. Positive in quadrant 1, negative in quadrant 2, positive in quadrant 3, negative in quadrant 4. I prefer to just write one I base formula, which is 1/3 BH cubed. And you can apply that about the y or the x-axis if you understand that B is always the dimension that's parallel to the axis of interest, and H is always the dimension that's perpendicular to the axis of interest. For example, if you have an area with a dimension M here and a dimension N here, then if you're finding IX, then IX is, and if this is touching the x-axis, then, well, even if it's not. So if it's up here, the centroidal I that's parallel to the x-axis is 1/12 B, which is M, H cubed, which is N cubed. If you're finding IY about the centroidal axis, then now the N is the base because it's parallel to the Y, and then M is the H because it's perpendicular to the Y. And then your I base formula about the Y-axis is still 1/12, or about the centroidal Y, is still 1/12 BH cubed, but now N is the base and M is the H. To me, it just simplifies the formulas. You don't need extra formulas if you just understand how to do that. For a triangle, for a right triangle, he gives an I bar, which is 136 BH cubed, which is the moment of inertia about the centroidal axis. He gives an I base, which is 1/12 BH cubed. He gives an I origin form for about the Y and the X, and this is IXY, about the X and the Y axes. He gives you this formula, but remember this formula is positive in quadrant 1, it's negative in quadrant 2, it's positive in quadrant 3, that's negative in quadrant 4. So this is product of inertia for a right triangle whose point touches the origin of the XY axes. He gives the I bar, X prime, Y prime, about the centroidal axis. So it's the product of inertia about the centroidal axis. But he doesn't tell you that depending on the orientation of this right triangle, the sign of this I bar can change. At the orientation that he gives it, at this orientation, that's a positive. But if the right triangle is oriented this way, that's a negative. This way is a positive, and this way is a negative. Remember, these are not quadrants. These are orientations of those right triangles. And so these are all their I bar XYs about their centroidal axis. But again, these will take on different signs depending on the orientation of the right triangles. He doesn't give those to you. On the right circle, or the quarter circle, he gives an I base, which is pi over 16 r to the fourth. He gives a product of inertia about the xy axis, which again I call an I origin form of IXY, and that's 1/8 r to the fourth. He does not give you the signs for this guy that if you use the I origin form of IXY, quadrant 1 is positive, quadrant 2 is negative, quadrant 3 is positive, quadrant 4 is negative. He does not give you an I bar XY formula at all for this quarter circle. And it's 0.01647 r to the fourth. And again, the signs of this guy vary depending on the orientation of the quarter circle. And so a quarter circle at this orientation is negative, at this orientation is positive, at this orientation is negative, and this orientation is positive. So this is probably not going to be on your test, but I'm giving this to you for completeness. And again, pointing out what he gives and what he doesn't give on the crib sheet. For half circle, you've got an x-axis, which is also the same as the x prime axis. You have a y-axis, which I would call a base. And then you have a y prime axis, which goes through the centroid. Ix is the same thing as Ix prime, which is pi over 8 r to the fourth. Iy is the same thing as an I base, in my view, which is pi over 8 r to the fourth. I about the y prime axis is, he gives it as pi over 8 minus 8 over 9 pi r to the fourth, and you can derive that. But I typically just list it as 0.1098 r to the fourth, so you don't have to do this math on the fly. And that's the I about the centroidal y prime axis. He gives the product of inertia of Ixy is 0, and I bar of x prime y prime is also 0. Both of these due to symmetry, because it's symmetric basically around the x or the x prime axis. And so these guys are both 0 for a half circle. Finally, for a hole or for a circle, you have the moment of inertia, I bar, which is also equal to Ix or Iy, is pi over 4 r to the fourth. And due to symmetry about the center, the I bar xy, the product of inertia, is 0 due to symmetry. And so you need to be able to understand, to be able to read the Hibbeler crib sheet for what he gives and understand what he doesn't give. I'm pretty sure the exam won't have things that he doesn't give on it, but you just need to be able to understand your crib sheet and know how to read it.